So good evening everyone. So this is the week 6 interactive live session for this traffic engineering course, and myself Suman Ganguly. So I am a research scholar at IIT Kharagpur. So the course instructor is Dr. Bhargav Maitra. He is a professor at IIT Kharagpur. So this week also we will do the same. We will first discuss some of the things which is already there or covered in this week 7 module basically, which is the pre-timed signal design procedure. First it will cover the basics Webster method, how to design a signal based on Webster method. Then it will come to the critical lane and time budget method. Once this is done, we will come to the ACM 2016 planning level analysis for signal design, right? And then finally the operational level analysis. So the detailed operational level analysis is not included here, since uh, because it involves a lot of formulas. So also there are less chance that you will get uh, questions or uh, in your exams or in the assignments also. I think there are not many questions from operational level analysis. Mainly these are the three things which has been covered or which has been given more emphasis on, because the concept is important in terms of operation analysis, but uh, we may not have to remember those formulas, right? So that's why it is important to know, but we may not be able to cover here. So first is the Webster method of signal design. So it's a traditional and older way to design a signal. So basically, the purpose of a signal design is to minimize the delay, the intersection delay, right? So suppose you are having an unsignalized intersection. Now you want to install a signal, but why do you want to install a signal, right? So because maybe your traffic volume becomes very high, or your movements, the different traffic movements became unsafe. So since this is became unsafe and traffic volume also high, so your intersection is may not be able to effectively means maybe you are facing significant amount of delays or while you are traveling or traversing through that particular intersection, or maybe there are unsafe movements that are occurring, right? So due to that, maybe we want to install a signal so that our delay is minimized as well as our safety is not compromised. So uh, there are two objectives. First is we have to minimize the overall intersection delay, right? And then the second is to also we have to improve the safety scenario. So now I already described some of the terms related to signal in the previous week 5 discussions, right? Like phasing. There is a call, it is a phasing. So why we actually do phasing? Why it is necessary to do phasing? So basically phasing means, because intersection is a shared space, right? So if I draw a intersection here, so it's a four-legged intersection, suppose, because there are four legs, right? 1, 2, 3 and 4. So now there are vehicles coming like this, maybe like this, and also maybe from here, right? So there are all the direction the vehicles are coming. Now which one to give priority, when to give priority, because if you are not restricting the movements and at the same time if your traffic volume high, then there are chances of collision, right, or conflicts. So that's why we want to separate out these movements. So now for that you want to install signal, and you want to decide that what is the phasing scheme, right? So suppose now for this movement, particular this movement, so what should be a conflicting movement, right? So this is a direct conflicting movement, right? So this movement, so we have to allow or restrict this movement, right? as well as if I have some vehicles like that, so it will also directly conflict, right? It will lead to a collision. So we need to restrict this movement as well as this movement, right? Whichever causes this direct movement for that particular movement. So that's why we have to design our phase effectively. So now what will happen if we want to separate each of these movements? So suppose there are 1, 2, 3 and 3 into 4 for each 12 movements, right? So now suppose because we want to improve the safety, so I want to segregate 12 movements altogether. So I want for each I have a green time, and now I want to design a signal. So what is the demerit? So demerit is your delay will be high, because whenever you are serving this and this, your all other movements are waiting. So now their delay will increases. So suppose imagine there is a scenario where volumes are relatively high at both the legs, as well as major and the minor both. Or if it is a major scenario, then it is always that in the both leg the volumes will be high. So there will be queued at other leg, right? Whichever leg is getting the red at that time. So we cannot increase the number of phasing in a rapid manner. So we have to judiciously decide what is the number of phasing. Now suppose I only use this kind of four-legged intersection, I use only two phasing, then what will happen? So obviously if you have only two phasing, means you are allowing suppose 6 movements at a time, and then you are allowing other 6 movements. So obviously there will be conflicts, there will be some conflicts points that will always be there. So now the less is also bad, the more is also bad, right? One is increasing your or compromising your safety scenario, other is increasing your delay. So what should be the optimal kind of uh, scenario or optimal kind of phasing, that we have to decide, right? So that's why there are different analyses that how to actually decide that what is the number of phasing. Should we go for a 2-phase signal, should we go for a 3-phase signal, should we go for a 4-phase signal, right? So that you have to be you have to decide as a traffic engineer or as a planning engineer, you have to decide. So once that is decided, now the question is how to even know that what is the signal length. So suppose here I can choose a signal timing of 60 seconds, even I can choose a signal time of 120 seconds, even I can choose a signal time as high as 280 seconds, 240 seconds, etc., right? So now how to choose this signal timing itself? Because if your signal timing is high, that means your green time is also high, and as your green time share increases along a particular movement, so there will be more delay in the other movements. Or the scenario may come that you have a green going on at a particular through movement, but there are no vehicles, but still you are giving green, and there are more vehicles which is waiting at the other leg, and you are not giving green to them, right? So this kind of scenario is not acceptable. So now you have to decide that how to actually design this signal. So that's why there are methods which are, one of the methods is Webster method of signal design, which actually deals with the optimal cycle length. What is the optimal cycle length? It is usually if I suppose whatever the phase number is, so it obviously it will depend on the phase number, but suppose I have fixed that I will take something like 3-phase signal I want to design, right? So now if you want to design a 3-phase signal, what could be your optimal cycle length, right? That will also determine your green cycle length. So now suppose the formula is what? Formula is simple, 1.5L plus 5, I think, and then 1 minus summation of that y. Here y means that I is phase, I equal to 1 to whatever n, if there are n number of phases. So it is obviously depending on the phase, right? So your phase number is, if your phase number increase, so there is a chance that this number is also increased. As your this number increase, this is lower. As it is lower, your signal optimal cycle length will be higher. So right, so obviously if you increase your number of phasing, so there are more segregation and you need more time for those phases to allocate, right? So obviously this will happen. So but here the scenario is how to design this, how to decide this optimal signal cycle lengths, and this is the Webster method of signal design, right? So so basically here what we want to do, we want to calculate this. So suppose, so if I remove this and draw, sorry, okay. So this is the formula. So basically we know that a cycle, total cycle time of any signal is consist of what? Green time, there is a green time, there is a red time, and usually there is also a yellow time. And also we know that something called AR or all red time, right? So these are the main things or main constituents of a signal time, right? So now here you have to calculate 1.5. So this is the empirical factor which is coming. Webster are actually proposed this, and also there are many modifications of this Webster method as well. But here we are considering about the old Webster, which is I don't exactly remember the year, but it is sort of old method of signal design. So now L is what? L is your basically 2 into n plus your red time. So 2 into n is depending on the number of phases. So basically L is the your total lost time. Lost time means, so suppose your signal is C and your lost time is L. So it is constituent of your green time. So C minus L equal to green, right? And this lost time, it will include your yellow time, your all red time, your usual red time, right? So this is called the lost time, total lost time. Now how to calculate this y? Y is, suppose you have this four-legged signal. Now your this volume is suppose 60 and your left volume is 100, right? So you have two lengths, and now your this volume is suppose 80 and your left volume is suppose 70. Like that you have, suppose there are maybe three phases, right? So now if your phase 1 is this, although this is not acceptable, but suppose your phase 1 is this, this movement is allowed 1 and this movement is allowed 2 and your maybe this movement is allowed 3. So now these movements will occur simultaneously, right? At the same time it will occur. I will give green. So how to decide what is the green time, right? So ideally all the vehicles along these three stretches has to be passed during that green time, right? So now how to ensure that? So now suppose your turning is 100 and now you have something called a saturated volume also, right? So what is the saturated volume? Is equivalent to capacity of that intersection, right? Why it is called saturated volume? Because only green time the vehicle can traverse, not that it is not acting like a unsignalized intersection. Unsignalized intersection, throughout any time the vehicle can pass. Here only green time the vehicle will pass, right? So that's why it is called, there are something some term is called, which is called the saturated saturated volume, which is different than your actual capacity, right? So then saturated headway, based on saturated headway, suppose your volume is 100, your saturated headway is suppose 200. So now your ratio is what? Ratio is half, means 0.5. But here maybe it is 60 your V, volume, observed volume, and your maybe 150 is your saturated volume. Saturated volume means you can consider it equivalent to a capacity, but because here I already told you that capacity will only be achieved if you consider only the green interval. So suppose right now this is the ratio, second 60 by 150. So this will come something like how much? something like it will come, and then here suppose 70 and suppose 100. So now whichever the ratio is maximum for this particular phase, we will consider this as y1, and if it consists of 3 phases, we will see that for each phases which is the critical movement, right, or critical v by c ratio. Why we need to determine critical? Because volume may not be sufficient, because v by c is actually representing your ability to pass along that intersection, right? So for each movement we have to calculate what is the v by c ratio, and which is the highest value is there. Based on that highest proportional value we need to design our signal. That means for that ratio it has to be there, right? So then it is called y2 and then your y3. So like that you have to calculate what is the your optimal cycle length based on your Webster method of signal design, right? So maybe we want to do some kind of Webster method related problems later on in this course. So then there comes, similarly to this Webster method, there is another method called the critical lane and type budget method. So this is also another method, right? So here also what it does, it instead of calculating directly what is CO, it is also calculating the critical lane volume itself, but it starts with that suppose we have the lost time of L per phase. So now suppose we have n phases, so total lost time is suppose n into L. Once we know that okay, total lost time is this, then we know that for this C cycle the lost time is L. For if the cycle length is 1, then your lost time is L by C, and your cycle length is 3600. So then this is your total lost time in an hour, right? Total lost time in an hour, because C will involve all the time, it is not the green time. So then as you know the total lost time T in an hour, then you also know the what is the effective green. Effective green is 3600 minus T, it is called the effective green, right? So as you know the effective green time, because you calculated the lost time, right? So now also you can say that suppose saturated volume exists, right? So if you divided this time T by your saturated headway of H, so what you will get? You will get the suppose the volume, right? And because we are considering only the critical lanes, so we will get the critical lane volumes, right? So once we know the critical lane volumes, so now we can observe that this is the maximum permissible volume. So if your actual volume is exceeding this scenario, right, so then you have to check that how to, or maybe you need to increase your lane, or maybe you need to increase your green time. So like that you can do, right? So this is called the critical lane and time budget method. So now then HCM method 2016, this is the third case. So here generally what we does, because if you remember we talked about the in capacity analysis chapter, so there are 3 types of analysis. One is called the planning level analysis, second one called the design level analysis, and third one called the operational level analysis. So if you remember, operational analysis was most complex one, right? It needs all the details, all the data, and need detailed calculations. Whereas in case of planning level analysis, uh, we may not need that kind of detailing, but we want a quick review of the situation, that how your system is working, what is the effectiveness and all, right? So this is what is called the planning level analysis. So here also we will focus firstly on the planning level analysis, right? So now suppose the planning means what? Suppose you have an intersection and you are feeling that intersection is facing many troubles, or it is also showing a history of road accidents over the years. So now you want to improve the scenario by installing a signal. So the first question is how to design a signal. So suppose what are the things that is known. So by field investigating, you can calculate what is the current traffic volume, what is the intersection area which is available, what is the number of lanes, or what is the width of those lanes. So those information are there with you, right? So now you want to design a signal from the scratch. So according to this highway capacity mill 2016, the first thing is that you have to decide that is your right turning movement is permitted right turning movement or protected right turning movement. So already you know that what is called, what do you mean by permitted and what do you mean by protected. So permitted means it is allowed at a particular phase. There is a phase, or there is a in a phase this movement, this right turning movement is also allowed. That is called the permitted, usually the normal scenario. But the rest of the times it is not permitted. But uh, no, that is called the protected, right? Protected means only at a particular means I am giving it under a means it will act as a, like, whenever this particular movement will occur, there won't be any conflicting movements at that time. So it is completely protected from any movements. So at what scenarios, if you imagine this kind of thing is possible. So suppose your right turning is causing maybe more harm, right? Your right turning maybe volumes are also high. So at that scenario we want to protect it all together, right? Or permitted means whenever that right turning movement is always open irrespective of the phase generally, and then the vehicle will check the gaps. If it is available, then it will cross over, right? So that is the difference between permitted and protected. So according to this ACM 2016, before you perform a or before you decide that you have to install a signal, you have to decide that for right turning movement, because generally right turning movements are critical, right? Because it will hinder the movement of the major through moving vehicles, right? So now for right turning movement, what should be your means what should be your idea, that should we go for a permitted signal phase of that particular movement, or should we do a protected phase? So there are some guidelines which is given, or some checks, like your turning movement should not be greater than this value, it should not be exceed this and all. So those are there in the PPT, right? So based on that actually it is given. So now the second thing is you have to convert your movement volumes to through PCUs, right? So suppose in an approach to an intersection, so there are certain through movements, left turning movements, right turning movements, all are happening simultaneously, right? So for a better calculation or better idea, we want to first this we need to convert the anyhow we need to convert the volumes into PCU, so that a standardized unit can be designed. So already we know the concept of PCU. So because there are varying effects, so you want to calculate the equivalent PCUs, right? We want to convert the normal traffic volumes into equivalent PCUs. So once we do that, the next option is uh, we have to convert also turning movements to the through movements, right? So how do you convert these turning movements to through movements? So basically there are many factors which are actually responsible for this. First is the effect of heavy vehicles. So suppose there are maybe at two intersections the flow is almost same. Flow means traffic volume, but at one intersection there are heavy vehicles. Heavy vehicle volume means the trucks are more high. So you can imagine the time take for that particular intersection with heavy vehicles, the time take to cross will be more, because there are heavy vehicles, it will restrict other movement as well, right? So actual your adjusted flow volumes or your green time should be increased, and it is as it is depending on the volume, so actually your volume should be increased, right? In case of intersection with heavy traffic, heavy vehicles. So uh, now you need to calculate this. That's why you need a adjusted traffic volume for this. So now what is peaking characteristics? So already you have heard about the factor of peak hour factor, right? So generally what happens, so we calculate hourly volumes, but there may be certain scenarios where even within that particular hour, 1 15 hour the variation is very much, and other 15 minutes the variation is not that much. So it will also create an imbalance, right? So average maybe is okay, but your that 15 minute will fail, right? And it will also lead to heavy means it, then your obviously at that peak 15 minutes your vehicle will not be passed through that signal smoothly, right? So obviously you need to adjust your uh, volumes, right, in order to improve the green time. So then the right turns and left turns, so see, generally our turning volumes are actually will take more time, right, to cross the intersection. So suppose there are scenarios where the traffic volumes are same almost, but at one scenario there are more turning movements, right? So if there are more turning movements, so actually it will take more time to cross, and if even if you are giving the same green and at the same flow, so there are less vehicle which will cross, right? So now the thing is you have to increase the green time accordingly, right? So that's what the thing, you have to increase your green time because your turning volumes are high, right? So your same so green is not same, right? So you have to improve it. So then you imagine similar scenario, at one scenario the parking activities are very high, so on street parking activities, so it will hinder the traffic movements, it will cause them to go slow. So now if you gave the same green, so same number of vehicles won't pass, so you have to increase the or adjust the traffic volumes accordingly. Your parking activities also will hamper or affect the green time, right? So then the lane utilization. So suppose the scenarios are, one is only through movement, other is through as well as your left turning traffic is occurring simultaneously from a lane. So if this is the scenario, obviously the same number of vehicle won't pass, because uh, mm, uh, your saturated headway, your saturated traffic volume won't be same. Your actual saturated field observed volume won't be same. So you have to again adjust your demand accordingly, right? So these are the things that you have to do before you decide, means before you means your calculated volume has to be adjusted to account for this effects, right? So now once you know that your this movement is protected, right turning movement is protected or permitted, and also you normalize, kind of normalize your volumes or adjust your volumes based on the actual existing field scenario, which is obviously different than your base scenario. So then you can now calculate what are the critical lane groups, right? So because critical lane groups means which are having the highest V by C ratio, right, based on a phase. So because we do not have a phase, so right now maybe you can decide ki okay, hypothetically maybe I am having some three phases. If I have three phases, so this kind of lanes are coming. So now I can calculate what is the lane or movement group here actually. So now I know that what is the V by C scenario, right? So now based on that V by C, we actually can assess for each movement, or is your intersection is sufficient, right? Or is your estimated cycle length, because once you know the critical length groups, now if you can calculate your L equal to suppose number of phases plus some values, then you can calculate, suppose based on Webster method you design a signal. Now you can actually check your whatever your cycle length is it sufficient, or your intersection is insufficient at that particular cycle length. So suppose your V by C is more than 1. So now you have to think that either you have to change your phasing maybe, or maybe you have to increase your cycle length, revise your cycle length, or maybe you have to means increase your number of lengths. So these are the things that you actually can do, right? So this is the scenario planning level analysis, right? So you can plan for that signal, and based on the planning accordingly you can actually decide what to do. So after we discuss this, the next part is operational level analysis. So basically, although I won't go into much details, but in case of operation analysis, what we do, we actually go for a more detailed thing. So here nothing is calculated by assumption. So if you remember last time also we told you that we have to how to calculate that lost time, because there is something called end gain, and how to calculate those. So each and every factor will come into account in case of this operational analysis, right? So, and also in case of general operation analysis may not be that complicated, but according to this HCM 2016, it is not very straightforward. So there are some complications which is involved uh, in this kind of operational analysis, right? So as right now there are no students, so I intend to wait for some time before I actually go with the actually question, means the problem solving sessions, right? So I will wait for some time, then I will do that. थोड़ा खा लेते हैं, भूख भी लग जाए ना. খেতে তো হবে, খেতে পাচ্ছ তো? একদম অফ করে মিউট করে বসে আছি, খেয়ে নিয়ে আবার আমি এখন চুপচাপ আছি।
ও স্টুডেন্টই নেই আজকে,
ঢুকেছিল দুজন,
চলে গেছে।
আমি ওইটা খেয়ে নি, আমি সুযোগ পেয়েছি।
হ্যাঁ
আমি বলেছিলাম যে since there are no students, so I will wait before I start the Q&A sessions বলে মুড়ি, আমি তো দেখে নিলাম ঢুকছিস, আমি ওটা বলে মুড়ি খেতে শুরু করে দিলাম। So welcome back again. So I have waited for long, I think 5 minutes. So now we can actually start this Q&A session by solving it. Okay. So first I want you to try and then I will be solving it. Right? So you have this intersection. It's a simple four-legged intersection, right? So it is a two-phase. We know already what is two-phase. I think we have two phase. Each phase we have given 3 seconds, 1 second, time loss 3.5, peak hour factor 0.95, right? So we need to calculate the value of summation y, means the total summation of ratios of approach flux to saturation flux for all the lane groups. And how to do it, right? So this is our volume 548, 548, 512, 512, right? So this is suppose one phase and this is the next phase. So for this phase, how do you calculate it? You calculate by 548 is your volume. So you calculate equivalent hourly volume by doing this. Whatever your volume comes, that volume by your saturation flow. So saturation flow is given for this total lane group, not for the individual per lane. Okay. So if it is so, then we have to do it into cross 2. Whatever the value we get, we have to divide it by 1200, and for that we will also do it 512 by 0.95, right? And then it will be southbound 1400. So this should be our answer. So let me calculate. So then we have to add it. So 548 by 0.95 into 2, 1154. Is the volume here divided by 1200. So 0.96 is the factor. And then for this, what will happen? By 0.95 is 538 divided by 1400 plus but this should not be greater than 1. That means it is per lane. If it is so, then we do not have to do this. That means our volume calculation will change to 576 by 1200. 0.48 plus 0.385 plus 0.385. So 0.86 or 87, like that. So also we wanted to go and check whether this is the actual answer. What is the, because it is solved there, so okay. So whatever we have done is right. Right? You can see it is 0.860 and 870. So we calculate it. So now for that particular example, we have to calculate what is the optimal cycle length. So how do you calculate the optimal cycle length? So the as per Webster method it is given. So your optimal cycle length C0, already you know that 1 minus 0.87, right? Here 1.5 into L, plus 5. So generally L is 2n plus R. Here it is a two-phase signal. So 4. Okay, or it is given that you have to see. Okay, so it is given actually, so we do not use to use this formula. So what is given is 3.5. So 3.5 into 2 is 7 seconds. 7 seconds. So we are getting our lost time equal to 7 seconds. If that is so, then what is the optimum cycle length? So generally L is okay, maybe directly it is given. So we have to check whether plus 5, 15.5 by 1 minus 0.87. 119.23, almost 120. Let us check whether it is correct or not, whatever we have done. So you can always check the results. No, it is not correct. So last time we have to add the all red time as well. So that's what my also inquiry is, because it's generally 2n plus r, but it is here, it is directly given. So it is not 120. So what we have to do, we have to increase this. 2n plus 2r means 7 plus your 112, 9. This is 9. So 1.5 into 9, 1.5 into 9 plus 5 by 1 minus 0.87, 142.30. 142 seconds is your optimal cycle. So because in terms of lost time, we have to include AR, all right, time per phase. So then the effective green for EB approach. So what is the EB approach? So this is the EB approach. So here we calculated the ratio of how much? It was calculated as 548 by 0.95 by 1200, 0.48. This ratio was 0.48 for this eastbound approach, your V by C ratio. So green time will be allocated based on your 142 will get, yes, based on the ratio of this V by C. Green time will be allocated. So then your 0.48 into 142, approximately it will be 71, but it will be like 69 or something. Let us calculate. 0.48 is 68.16. 68.16 is your effective green time. Okay, it is not effective green time because we did not calculate. It is not effective green because we did not calculate the green time. We calculated the total time. So 142, we have to negative the total time means 7 plus 2, 9. So once we do that, we will get 142 minus 9 means 133. 133 into 0.4. So this is not the correct answer. 133 into 0.4. So 133 into 0.4. So maybe 63 or 4. will be the right answer. Can we check? Yes, we can check. So just we will again check what is the answer with the actual answer. Okay, so it is coming at 67 point. So our cycle length we have calculated as 142. So it's a range of this 142. So if it is 142, then our correct answer range is 67 to 75. So what we get? Okay, we did not get it. Why? 142 minus 9. Oh. So since the eraser is important. Okay, maybe it is not working somehow. But because the total ratio is not necessarily 1, so we have to divide this. Why it is not working? Discard. Oh, okay, it is automatically saved because last time I did that. Okay, so because it's a ratio of 0.48 by 0.86, this is the ratio, right? So now if we calculate 0.48 by 0.86, so 0.56 times 133, 74.23. So this was the range that is also given, 74, right? So now this is the lane configuration and demand volumes, it is given, right? So it is an exclusive right turn lane, it is a shared through and right lane, and it is the shared, and this is the demand volumes which is also given, right? So here it is saying that lane configuration and traffic volumes for each movement are given. Percentage of heavy vehicles for all the movement 10%, EPH of 1.09, opposing volume traffic this, number of opposing volume this, no parking activity this, it is the heavy vehicle. Following segments are true with respect to the right turn operation. So what is the value for equivalent through movement flow rate for right turn movement? For right turn movement is 225. What is the equivalent through movement flow rate? So you have to include the adjustment factors. One. So you have to calculate what is the percentage of heavy vehicles. CPHF is 1.09. Then opposite traffic volume is 5 to 6. Then okay, let's go to the actual solution. If you see, if you can go here, you see this is the adjustment factor formula. So you have to calculate what is the EHV using this formula, right? It will come out to be 1.12, right? So once it is you calculated 1.12 for protected right turn operation, your ER is given as 1.05 and your this is given as this. So now your adjusted volume is 225 is your actual volume was there, 1.12 is your EHV, 1.09 is given, 1 is also given, 1.05 is this protected right turn and 111. So basically 1.05, so 288 is 88 your is an equivalent traffic volume per hour. So is 288. So here if you see it will be 288. You have to include this factor and EHV factor as well as other factors like E other one and those things. Okay. So then here it is not there, but maybe we can discuss by here itself. So now if you see here that which of this is already you can copy here and you can paste it here. So for this, which of the following statements are true with respect to right turn operation? So it is about this 225 volume. So which of the thing is true? So right turn movements require permitted operation. If it is greater than some value, then only you can see. So it is not greater than 260, so it should not actually. The condition 1 is satisfied, therefore a permitted right turn operation must be allowed. These are the same thing, I think. Condition 2 is satisfied, protected. Condition 3, okay, let us go to the question. Is there something else that has to be known? So condition 1 is what? Your right turning volume is greater than 240, which is not satisfied here. Your condition 2 is because your yes, it is 225 and it is exclusive of this. Then your VRT into V0 it should be greater than 90,000. So here your condition 2 is satisfied. Your 225 into 526. 526 is your opposing traffic volume. Condition 3 is there is more than one right turn lane on the approach. No. Since one condition is satisfied, a protected right turn operation must be provided. It is not a permitted but a protected. Okay. So because condition 2 actually refers to what? One scenario is your right turn traffic volume is itself high, right? Then another scenario is what? Another scenario is your right turning traffic volume multiplied with your opposing traffic volume, that itself is high. So what does it signify? So if that is the case, your opposite movement traffic volume is also high, that means there is a chance that collision will occur, right? Because your that multiplication factor is very high. So that's why for that we need a protected right turn, not permitted. So suppose you have more than one right turn lane, so there it may not also cause that kind of inconvenience. Like suppose you have a you have a one so you have two scenarios. In one scenario there is only one right turn lane, in another scenario there are two right turn lanes, right? So in this case, in one right turn scenario, if there are too many vehicles which are accumulating, because there are opposite traffic volumes are very high, so it may not be able to get through, so it will stuck there and queuing will occur back, like vehicles will accumulate and there will be queuing, right? It will also impact the through movement vehicles of that particular movement, right? But versus you have suppose two right turn lanes and with similar traffic volume, so there is a chance that vehicles will store there and will not create disturbance to this do these movements, right? So based on that, that time you may allow a permitted movement to be sufficient. You may not need a protected movement, because in case of protected movement, because your movement will become unsafe and also will create chaos to your that related movements, right turn related movements, so that may actually lead to difficult. So then we can finish this, because since the students are less here and you are not asking any questions, so it is also very difficult to know actually that what is your actual concern and what are the areas that I should be more focused on. And since it is already means there in your actual course, so I do not want to repeat all the things, because it may not be required, as well as you may feel bored also, right? So I will encourage that you start interacting more, rather than a pre-recorded sessions where people usually just talk and then you do not have any chance to actually interact or ask questions like what happens in the actual classrooms, right? So maybe I will wait, so you, if you want, you can ask any questions, or maybe I will also see what are the some important questions. Also these questions, see, there are also operational analysis questions, but the thing is we did not go into the details, because see, there are formulas, right? There are only formulas, you have to use the formulas. It is nothing that you don't know, but you have to use this formula. So because we know that it may be difficult for you to remember these formulas, so we did not even include this type of examples in the final exams, as well as in your actual uh, your assignment questions as well, right? Okay, so these are all those questions. uh, okay, so also you see, in a case of this operational analysis, so actually a new concept, it's not radically, means it not entirely new, but it's a kind of new. So there is a concept called Q storage ratio, which has been introduced by your HCM 2016. So what it says that what is the uh, length of the bay, or the suppose turning lane in meters, what is the length which is available, and what is the length of actual queue. So based on that, which is called a storage ratio, Q storage ratio, so based on that actually they want to uh, uh, evaluate the performance of the different movements, right, or movement groups. So here also I think based on that, here actually there is something has been given. So how do you determine the delay at a signalized intersection? So actually how we discussed that in terms of signalized intersection, we have some three types of delay: D1, D2, D3, right? One is your random delay. So suppose you are coming and you are just stuck in the signal and you will leave, right? So that is one type of delay. Another is, suppose your demand is exceeded your capacity. In that case also you may incur delay, right? So that is another type of delay which is called the overflow delay. Another is the third one is the initial queue delay. So because you have a sustained oversaturation which is going on, so oversaturation means your demand is greater than your capacity. So if for a long time period your demand is remains greater than your capacity, then what will happen? There will always be queue, because your signal system may not be able to uh, may not be able to serve that much of volume. So there will always be queue. So suppose your your green starts and you are reaching to a signal, you are seeing that already there are vehicles that are queued once it is started also. So you are coming from the upstream signal, but you are seeing the downstream signal. There is also always there is some queue is so never your signal is free of queue uh, on those situations, right? Because your demand is always consistently greater than the capacity. So there is a less chance that uh, uh, your stability will be there, because it is instability. So there will be instability, right? As long as your demand is always greater than your capacity, right? But suppose the scenario is like this, where uh, you have initial queue, but because over time your demand is reduced or reducing, so now you are seeing your queue is start clearing, right? So those scenario actually eventually it will be stable condition will be coming back, right? But in previous case the stability won't come, it will be like that. So here you see the uniform delay means it's a kind of what is if I am traveling a vehicle, is the intersection, if the intersection is an undersaturated intersection where demand is less than the capacity of that particular intersection, so what is the delay? That is called the uniform delay, right? So here it is given that what is the uniform delay for this lane group. So see, this is the formula. PF is a progression factor, which is 1 here, because it's an undersaturated scenario, uniform delay, so there is no progression factor, right? Means it will not impact that much, it is always 1. It will not increase your delay, that is the thing. So then the rest of the things is same. If you see 0.5 c into 1 minus g by c is usually we calculate how the what is the green time, right? And then it's square by 1 minus, so it is a standard formula which is given, and based on that you can calculate what is the uniform delay. So then you also see the incremental delay, so that is the delay not due to a sustained oversaturation, but due to some suppose uh, because means what happens, your demand is not always same then over the period of time, it will fluctuate. So due to this fluctuation there will be some kind of incremental delay, not uniform. It is not that almost similar number of vehicles are always coming to an intersection, right? It is not so. So it is not always uniform is the ideal situation, right? So that's why there is something called the incremental delay, right? So this is the equation of incremental delay, and if you know the equation you can always solve it. So x is your v by c ratio. Once you know that, other things are given, and here that is not there, your d3 component, right? So it is only d1 and d2, right? So based on control delay, actually I think it is not an oversaturated. See, it is written for this problem that assume initial q delay is equal to 0. So that's why third component we we won't be we do not need to calculate actually, right? So based on that, what is your level of service? So now you add it and you checked it. Now see, your is 44.2 seconds, which is greater than and less than within this bound, which is corresponding to your level of service D bound, right? So this is called your total delay. So then we can come to this question as well: which of the following statements are correct with respect to back of the queue, right? So queue is occurring at the back. What is happening, right? So back of the queue size includes partially stopped vehicle. So generally here, as per ACM 2016, whenever we are calculating queue storage lane or the average queue length, we do not actually include this partially stopped vehicle. What is the partially stopped vehicle? So it's like vehicle are coming, it is already red, where vehicle is coming. When it is near, it will just maybe slightly slowed down or stopped, and then it is immediately leaves, because already there is a yellow and then green, right? So those kind of vehicles we won't calculate at the queue. Queue means it is fully stopped. That's why it is queuing, right? But at that transition period, whichever vehicles are actually going through, we won't uh, consider those vehicles, right? So then the back of the queue represent maximum backward extent of queued vehicles during a typical cycle. So back of the queue, he is saying, represent the maximum backward extent of the queued vehicles. You can say it is obviously it's a correct statement. Back of the queue represent the maximum backward extent of the queue, obviously. Then acceleration deceleration delay is used to distinguish between a fully and partially stopped vehicle. Acceleration deceleration delay is used to distinguish between a fully and partially stopped vehicle. Okay. Okay. So your acceleration deceleration delay means, suppose you have a signal, and if signal is red, so you will decelerate because your signal is red, and then you will stop. Then once your green time is on, you want to move forward. Then once you then you reach to this desired acceleration. So now the question is your acceleration deceleration delay distinguishing the fully and partially stopped vehicle? uh, Fully and partially stopped vehicle. Actually your acceleration and deceleration points, so it is at the point where it starts decelerating, and it is the point it is start accelerating. So your deceleration point may sometimes overlap for this partially and fully stopped vehicle, but in case of your acceleration point, this partially stopped vehicle will reach the acceleration point quicker than your actual fully stopped vehicle. So it can be used to distinguish between your fully and partially stopped vehicle. So it is also true, right? So third term of back of queue means the Q3, which corresponds to the initial delay, right? The sustained oversaturation accounts for delay caused by signal cycling through its phase. So what is saying that it accounts for the delay caused by signal cycling through its phase signal. No, it is not true, because Q1 does this, right? Q1, not Q3. Q1 is your vehicles are coming at uniform flow, suppose, and then you are stopping. So your Q1 is accounts for that type of queue, whereas your Q2 is due to the fluctuations, randomness, right? And Q3 is if there is a oversaturation or initial queue. So it is not true. So here also we find that B and C are only true. It is here, it is only true. Here also it is given that which of the following statements are correct with respect to Q at the end of analysis period. At the end of analysis period, considering initial Q, so there is an initial Q and it is the end of the analysis period, and the V by C ratio. Okay. So if you want to try, you can try as well. So if your initial Q is 0 and your vehicle volume is greater than your capacity, there will be no Q at the end of the analysis period. But there will be Q, na? Because your V is greater than C. So there should be Q. So it is not correct. But if your QB is greater than, so there is always already initial Q is present and your V is greater than your C, and the Q will be greater in size than the initial Q, obviously, because your V is greater than 0, so it will accumulate, your Q will accumulate, right? So it will be greater than the capacity. Now suppose third scenario is your QB is greater than 0 and V is less than C, right? So if the scenario is like that, so then what is the Q status? The Q of the will be greater than, no, it will be less than, right? Because although you have a Q, but the next cycle is your volume is less than your capacity. So if the scenario is like that, obviously your Q at the end of the analysis period will be lesser in size, right? It will reduce because your volume or demand start, it is reducing, so it will always be reduced. So then the next is, if your QB is greater than 0, means you have Q at the start of the analysis period and your V is less than C, then Q will be lesser. Okay, that's what we are discussing. So your correct answer will be D, as well as your correct answer will be B, right? So it is because it is self-explainable, right? So then if we have something more to discuss based on this question, so already I have discussed the signal timings and then the Webster method, how to do it. So actually what is missing, that we should actually can include one the example with, I think, critical time budget method, that we have not included, right? But I think one problem is, although they are in the PPT, so you might want to look into that PPT as well, right? So from my side, I think I have nothing more to share with you, unless you have something that you can ask, that can be done, or I will wait because we still have time. So maybe I will wait for some more time before we close the session. So I will wait if someone has some queries, or some new student at this time also wants to join. So I will wait and then I will end this session for today. So is there any questions regarding anything that you that have been covered in this week? 7 is the interactive session, but your course, based on your NPTEL course, it will be week 7, right? So it is week 7, traffic signal control design, with particular focus on the pre-timed signal design or the actuated signal design, which is more complex, your actuated signal design. So I am waiting for your responses. If you have any queries, or anything you might want to ask, you can ask. I'm planning to wait up to 7:30, not 8, because I don't think that no means any more student will join after 7:30 for this interactive session. So I will be waiting till 7:30, then I will close this session, right? And we obviously will meet on the next week. Next week also we shall continue this signal control, and we will finish the signal control, right? And then we move forward to the traffic management measures on the week 8 in the NPTEL course. And week 8 or no, week 8 is about the signal. Week 9 is we will go to that traffic management module, where we will be learning about different traffic management measures using ITS, without ITS, the parking management measures, bus priority measures. And then we will enter into the week 10. 10 is also I think week 9 as well as 10, or do we have 2 modules of signal control left? Maybe we have, I think, 2 modules of signal control that is left. So there are maybe 4. Oh, no, I was missing the car following theory. So your week 10, week 9 is about car following theory after ending the signal at week 8. And then once the car following theory is done, we will enter into the traffic management options. And after traffic management options, the last 2 weeks, that is week 11 and week 12, it is about the traffic safety aspect, right? So first module is about the basics of traffic safety. Then comes to the what do you mean by black spot, and then how to do or how to conduct safety audits, right, on the different national highways. What are the types of audits, and then different methods for accident investigation, accident frequencies, and then different machine learning algorithms, how to leverage those machine learning algorithms to actually calculate the traffic safety. So in this way it will go, or it will move forward, right? That's all about this syllabus. So any questions, any more questions regarding this week 6 interactive session on traffic signal control? This session is particularly about the pre-timed signal control based on Webster method, which we discussed, then the critical time budget method, and then the third one is the planning level analysis as well as the operational level analysis based on the Highway Capacity Manual 2016, right? So shall I wait for more time, or shall I leave? So maybe because there are no questions and I waited long enough, and I don't think that any more people will join right now, and I have already finished my discussion part, whatever I wanted to share with you people, that I have done. So once it is done, so maybe I will end this session right now, and maybe we will join on the next week, right? So So thank you for joining in and listening to me patiently. So we shall meet on the next week, and we will finish this signal control part on the next week. And basically I think next week you have something called signal coordinations, which is not dealing with isolated signals but a series of signals. So how to coordinate, how to design a signal so that a vehicle is stopping at the upstream intersection does not have to always stop in the downstream intersections, right? So it should freely should move through the signalized corridors. And what do you mean by platoon ratio, then what is the discharge, right? So those things will be there in the next class. So we will discuss that. Whatever I feel that it is necessary, I will discuss. So okay, then we are ending the session for today. Thank you. Bye.